To wrap up the chapter, I just want to discuss briefly some alternate mechanisms by which some reactions can happen. So the two mechanisms I'm going to talk about here are nucleophilic aromatic substitution and the Benzyne mechanism, or elimination addition as it's called in the textbook. Oops. All right, so our first mechanism, nucleophilic aromatic substitution, can happen in cases like this. So this is a good way to make phenols. If you'll notice, the phenol group is one of the groups that is completely missing from our synthetic process right now, or from our toolbox rather. So if I have ortho-nitrochlorobenzene and I treat it with sodium hydroxide followed by an acid, I'm going to make a phenol group. Here we've substituted the chlorine atom with the OH group. Now just remember that this cannot be normal SN2 substitution, as we have an sp2 hybridized carbon at the aromatic ring. So this type of mechanism will happen when we have a leaving group, which is usually in these cases a halogen, and this is going to be when the leaving group is specifically ortho or para to a very, very strong electron withdrawing group. The most common case where we see this type of reaction is if we have a nitro group. So what's happening here? Well, if we treat this compound, our starting material, with hydroxide, the hydroxide group is actually going to add to the aromatic ring as a nucleophile. Now, the reason why we need the electron withdrawing group to be ortho or para to the leaving group is that when the nucleophile comes in, it's going to serve as a refuge for those electrons. Since this step breaks aromaticity to produce a non-aromatic intermediate, this is the rate-limiting step. And you can see here that we get a relatively stable species with a negative charge on a very electronegative oxygen atom. So that negative charge is highly stabilized by resonance through the electron withdrawing group. This intermediate has a name. It's called a Meisenheimer complex. Next, we regenerate aromaticity by kicking out the leaving group. So that negative charge collapses back down, the leaving group leaves, and we have our phenol. Now, the important thing to remember is that under the conditions we've given, we still have a lot of strong base hanging around, so we're going to remove that phenol proton to make a phenoxide ion. This can easily be removed by a workup step, similar to what we saw for Grignard additions back in Organic 1. So this mechanism is sometimes noted as this, SNAR, because it's called nucleophilic aromatic substitution, due to nucleophilic substitution taking place specifically at an aromatic ring. All right, the other way to make phenols is by taking something like chlorobenzene. Now, if I take chlorobenzene and I take potassium hydroxide and I just cook it, and I mean really cook it, heating it up to about 350 degrees C, followed by an acid workup, I will also get a phenol. So this was the subject of a lot of arguments for a long time. What is the mechanism of this process? Is it SN2? Is it nucleophilic aromatic substitution? So in order to sort of elucidate the mechanism, we're going to do a labeling experiment where we place a carbon-13 label where the leaving group is. Now, in the product, as you'd expect, we do observe the label being retained at the carbon where substitution has happened. But also, weirdly enough, we get that label at the carbon next to where the substitution happens as well, and we get about a 50-50 mixture of these two substituted products. So what is going on here? Well, after a lot of argument, the mechanism that was finally proposed for this involves hydroxide acting not as a nucleophile. Oh, sorry, right, this is not nucleophilic aromatic substitution because we do not have that very strong electron withdrawing group. So the way this works is very different. Hydroxide acts as a base, kicking out the leaving group. This reaction should look familiar. It's an elimination. And that produces this intermediate here, along with water and the chloride ion. So this intermediate is called benzyne for obvious reasons, and this should make you cringe a little bit by looking at it because we know that a six-membered ring cannot incorporate a triple bond. It can't be linear. It cannot happen. So this does not behave like a normal triple bond, and it can accept a nucleophile to produce a carbanion. So this gives us a phenol group right next to a carbon with a negative charge. This is a ridiculously strong base, so it'll very quickly transfer the proton from the oxygen to the carbon, giving us again a phenoxide ion. This can be protonated by workup to give us phenol. This is one of the few ways that we have to make unsubstituted phenols. So how does the labeling experiment explain this? Well, if we start with benzyne with the isotopic label, if we start in the middle of the mechanism, the nucleophile could add to either side of the triple bond because there's no difference in terms of the stability of the intermediate that we make. So what we predict is that we get exactly a 50-50 mixture of the two possible products. So make sure you work through Chapter 18, Section 15 in the book. This talks about how to identify which type of mechanism is happening, because this sort of mechanistic elucidation is important to be able to predict if a reaction will happen and where the reaction will happen as well.